when the number of carbon atoms is increasing, that means when we are moving to higher alkanes, number of carbon atoms will increase, hence the mass will also increase. Hence, more boiling point is required. Methyl radical combines with chlorine radical and forms methyl chloride or chloromethane. If it undergoes complete combustion, it forms carbon dioxide and water. Now, if it undergoes incomplete combustion, that means it is not completely having a good supply of oxygen. So what happens in this case? Instead of forming carbon dioxide, you will get carbon black. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 2 of the chapter Hydrocarbons. So in the last session we studied about the introduction to hydrocarbons and then classification of hydrocarbons, right? And then we started studying about alkanes, right? So in the last session we studied about the methods of preparations of alkanes. So in today's session we are going to study about the physical properties as well as chemical properties of alkanes. Right? Okay. So first let's begin with the physical properties of alkanes. So the alkanes up to 4 carbon atoms are gases. Okay. So C1 to C4. What does C1 to C4 means? It is alkanes having 1 carbon atom to 4 carbon atoms. That means 1 carbon atom, it is alkane, right? 2, it is 1 carbon atom, it is methane, right? And C2H6 is 2 carbon atom, which is ethane. Then you have C3H8, that is propane, and C4H10, right? So these are the first 4 carbon atoms. So that is what is written here, C1 to C4. The alkanes which is containing 1 carbon atom to 4 carbon atoms. They are the lower members of alkanes. So they exist as gases, right? Now alkanes up to C17, that is from C5 to C17. Okay, the alkanes having carbon atoms up to 17, they exist as liquids, and the still higher members, that is more than 17, they are having high molecular mass, right? And they will exist as solids. So the lower ones will be gases, then till 17 it will be liquids, and higher ones will be solids, right? Now alkanes are insoluble in water. They are not soluble in water, but they are soluble in organic solvents like benzene and ether. Right. Next point, the boiling point of normal alkanes increase with increase in molecular mass, and it will decrease with branching. That is, as branching increases, boiling point decreases. Okay. So this point is important. Let's understand. The boiling point of alkanes increase with increase in molecular mass. So increase in molecular mass means, yes, the number of carbon atoms is increasing. The molecular mass is also more. Right. When the number of carbon atoms is increasing, that means when we are moving to higher alkanes, number of carbon atoms will increase. Hence, the mass will also increase. Hence, more boiling point is required. Right. More temperature is required for the alkanes to boil. So, boiling point means what? Yes. What is happening when it is boiling? Yes, the liquid is getting converted into gas, right? So the bonds are to be broken from the liquid state so that it can get converted into gaseous state. So what happens here? When the mass is more, we need to apply more temperature, right? The boiling point also in turn increases. Right. So that is how we can relate that when the mass increases, more temperature is required to break the bond so that it get converted into gaseous state. Now what about this one? As branching increases, boiling point decreases. Now why is that? Let's take the example of butane. CH3, CH2, CH2, CH3. So this is butane. Okay, another isomer of butane also we can draw, that is the CH3, we can put it as a branch. So how it will be? CH3, CH3, CH2, CH3. Okay, so this is another isomer of butane. So this is 2-methyl propane, right? So what is the difference you can see here? The branching has increased in this case, right? The branching has increased, but what is the important point? The number of carbon atoms is still the same. It is just an isomer, okay? So the branching has increased. So when branching has increased, what has happened? The surface area has decreased, right? Earlier it was a complete open chain. Now you have got a branch here. So the surface area has decreased. So when the surface area has decreased, it becomes easy to boil the alkane. That means the boiling point, only less boiling point is required. No much temperature is required to break the bonds and convert it into gaseous phase. Okay. So here the reason is because the surface area decreases. When branching increases, surface area is decreasing, right? So let's take the example of pentane also. CH3, CH2, 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 CH3. So now one isomer I am going to write. I am going to make this as a branch. So it becomes CH3, CH2, CH, CH3, CH3. Right? Now I can make one more branch out of it. CH3, 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 CH3. So in all these isomers, the number of carbon atoms is still the same. All are having 5 carbon atoms. But as you can see, now in this, all the CH3 groups, methyl groups are attached to the same carbon atom and they have a very small surface area. Hence, the boiling point also decreases. So, when the molecular mass increases, boiling point increases, and when the branching increases, the boiling point decreases. So, I hope you understood the reason also. Now, moving on to the chemical properties of alkanes. Okay. So, we are moving on to the chemical properties. The first one is halogenation. So, we have already studied when we were studying about the methods of preparation. What does hydrogenation means? Addition of hydrogen. Dehydrogenation means removal of hydrogen. Right? Decarboxylation means removal of carbon dioxide. So, same way, what will be halogenation then? Yes, we are going to add halogen here. Right? So, let's see. Halogenation takes place either at high temperature, 573 to 773 Kelvin, or in the presence of diffused sunlight or ultraviolet light. So, the reaction will happen at high temperatures or else in the presence of sunlight or UV light. So, let's see what is the process happening here or what is the reaction. Okay. So, let's take the simplest alkane, that is methane. First, what is happening? We are going to add halogen into it, that is chlorine we are taking. So, what happens here? So, we can say also call it as chlorination. Specifically which halogen we are adding, we can call that name as well. Here we are going to do chlorination. So, what happens? One hydrogen out of this will be substituted by chlorine. So, it will become CH3Cl and the Cl removed, one more Cl is here and the H removed will together become HCl. Now, this CH3Cl further reacts with another molecule of Cl2 to form CH2Cl2. One more hydrogen is removed, another chlorine atom is being substituted. So, we will get CH2Cl2 and again HCl. Right. Now, the CH2Cl2 combines with another molecule of Cl2 and forms, right. Again, one more hydrogen atom will be removed. What will happen? Cl3, it will become Cl3, right. So, you will get chloroform. CHCl3 is called as trichloromethane or else it is chloroform, right. So, this is the molecular formula for chloroform, CHCl3. Now, moving on to the last step. What happens? The final hydrogen atom can be replaced by another atom of chlorine and finally, you will get tetrachloromethane, CCl4. Now, is there any other hydrogen atoms to be replaced? No. So, the reaction will end here. So, I hope this is clear. So, now we are going to see the mechanism of this reaction. So, there are basically, it's a free radical chain mechanism. You already know what is free radical. So, we are going to study 3 major steps here. One is initiation, by which the free radical chain mechanism starts. Okay. That means in the beginning how the radical is going to be formed. Then the next step is propagation. The reaction will proceed. And finally the third step is termination, where the reaction stops. So, as I said now, the reaction is a free radical chain mechanism. So, let's understand the various steps of this reaction as well. So, this mechanism of halogenation is very important. So, as I said, the first step is chain initiation. We are going to start the reaction. So, chlorine molecule absorbs energy from sunlight to give chlorine free radicals. So, initially it was Cl2, right? You can see here it was Cl2. Now, this Cl2 absorbs, the chlorine molecule absorbs energy from the sunlight or UV light and breaks into chlorine radicals, right? Chlorine free radicals. Now, that is the initiation step. So, you got your radicals. Now, it is going to undergo chain reaction. That means the next step is propagation. First is initiation, second one is propagation. So, chlorine free radicals reacts with methane to give methyl free radical and HCl. So now this chlorine free radical which is formed in the first step, it will react with methane. Okay, and this H nu stands for the light, right? H nu stands for light. Okay, and it forms methyl radical and HCl. It forms CH3 radical and HCl. Again, what happens? See, it is CH4, right? It will form CH3 radical, and the H which is left out from here, it will combine with the Cl radical. So what happens? HCl will form and the radical will be shifted to CH3. So that is how you are getting methyl radical and HCl. Now in the next step, what happens? Methyl free radical. Now this radical, right, it will attack chlorine molecule to form methyl chloride and chlorine free radical. That means now the methyl radical, right, it will combine with Cl2 molecule and form methyl chloride and chlorine free radical. So again you will get chlorine free radical. Again the procedure will repeat. So what happens? This is why it is called a chain propagation step, because the process or the reaction keeps on happening. So how do we terminate this? We have to end, right? Finally we have to obtain our products. So how do we end in our final step? So let's see. The last step is called as termination. The free radicals, whichever free radicals are formed, they will combine with another free radical and form the product. So let's see. Chlorine free radical will combine with chlorine free radical and form Cl2. Okay, that is Cl radical combines with Cl radical and forms Cl2. Right, okay. Now, methyl radical combines with another methyl radical and forms, yes, ethane, C2H6, right. Now, another possibility, methyl radical combines with chlorine radical and forms methyl chloride or chloromethane. Okay, so I hope the mechanism is also clear. The first one is chain initiation, where the chlorine free radicals are formed. Now from the free radicals it will react with methane and form methyl radical. Next, the methyl radical will react with Cl2, a molecule of chlorine, to form chlorine free radical again. Now the chlorine free radicals will combine and form Cl2. Methyl radicals will combine and form ethane, and methyl radical and chlorine radical combine and form methyl chloride. So these are the three steps: chain initiation, chain propagation and chain termination. So this is the first chemical property, that is halogenation, right? Okay. Now moving on to the next one, combustion. So you already know what is combustion, right? So alkanes also undergo combustion. Let's see. Alkanes on heating with air or oxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. Okay, so what is happening here? Yes, alkanes on heating. Okay, so what is combustion? We are heating alkanes on the presence of air or oxygen. We'll get the products carbon dioxide and water, and there will be a high evolution of heat as well. So let's see. The methane has been taken here. The simplest alkane combines with oxygen and forms carbon dioxide and water. So this is a balanced chemical equation. And you can see delta H is negative. That means it is an exothermic reaction. Exothermic reaction. Energy is released in this reaction. Evolution of heat. So due to evolution of large amount of heat during combustion, alkanes are also called as fuels. Okay, they are also used as fuels because they emit or heating of alkanes end up in the evolution of a large amount of heat. Hence it is also used as fuels. Okay, so this is called as combustion. Alkanes on heating in the presence of air or oxygen gives carbon dioxide and water. Now the next one is incomplete combustion. Now, if it undergoes complete combustion, it forms carbon dioxide and water. Now, if it undergoes incomplete combustion, that means it is not completely having a good supply of oxygen. So, what happens in this case? Instead of forming carbon dioxide, you will get carbon black. So, let's see. Combustion of alkanes carried in limited supply of air. Okay, you only have limited supply of oxygen. In case of combustion, you need excess of oxygen. But in case of incomplete combustion, you don't have enough amount of oxygen. So what happens in this case? It forms unburned carbon particles, which is called as carbon black, which is used in the preparation of ink printers, yes, printer ink, in that it is used. Okay, so it is called as carbon black. Instead of carbon dioxide, you will only get carbon black. So the reaction is methane combines with oxygen. If it undergoes incomplete combustion, you will get carbon, which is the carbon black, and water. So instead of carbon dioxide, you will get only carbon. Right? The next one is controlled oxidation. Okay, so alkanes on heating with regulated supply of oxygen at high pressure and in the presence of catalyst give different products. So alkanes can undergo oxidation, but based on which catalyst we are using for the oxidation process, you will get different products. So this is important. Methane, that is your alkane, when combines with oxygen, when reacts with oxygen or undergoes oxidation in presence of copper at 523 Kelvin and 100 atm. 523 Kelvin is the temperature, 100 atm is the pressure. You will get methanol, CH3OH. You can see the OH here, that means it is an alcohol, right? So it is a methanol. So if you are using, or if alkane is undergoing oxidation in the presence of copper at 573 Kelvin and 100 atm pressure, you will get methanol. Now the same alkane undergoes oxidation in presence of molybdenum oxide. Okay, molybdenum oxide, what happens? You will get methanol, you will get an aldehyde and water. See what happened here now? The same alkane is taken, but the catalyst is different here. So in that case, you will get, in first case, you will get alcohol, second case, aldehyde. Now the next one is ethane is taken, and ethane undergoes oxidation in presence of manganese acetate. Okay, what happens? You will get ethanoic acid and water. So in three cases, three different catalysts were used. You got alcohol, aldehyde and carboxylic acid. So this is what happens when alkanes undergo oxidation in presence of different catalysts. Right. Now, ordinary alkane resists oxidation, but alkanes having tertiary hydrogen atom can oxidize to the respective alcohols by potassium permanganate. So usually alkanes resist oxidation, but if they are having tertiary hydrogen atom, they will form alcohol in the presence of potassium permanganate. So as you can see here, CH3CH, okay, CH3 thrice CH, that means CH3, CH3, CH3. Okay, so it is having tertiary hydrogen atom. Then what happens? Yes, in the presence of potassium permanganate, it can undergo oxidation, and instead of H, you will be getting OH. That means it can form a tertiary alcohol. So I hope that is also clear. Now moving on to the next one, isomerization. So you're already familiar with how to draw the different isomers for a particular organic compound, right? You have already studied this in organic chemistry. Now how these isomers are formed, or what is this process of isomerization? Let's see. So alkanes on heating in the presence of anhydrous aluminum chloride and hydrogen chloride gas, they get isomerized to branched chain alkanes. So for example, we have taken hexane here, CH3, CH2 4 times CH3, that is hexane, right? CH2 4 times it is repeating, that means total 6 carbon atoms. Now what this N stands for is, it is normal hexane without any branches, right? So normal hexane in presence of anhydrous aluminum chloride and HCl gas, what happens? Isomers are formed. That means it creates branches. So one possibility is 2-methyl pentane, right? 2-methyl, 1, 2, and there are 2 carbon atoms here, 3, 4 and 5. So you will get 2-methyl pentane. Another one is 3-methyl pentane. It will form its isomers. So this happens when it reacts in the presence of what? Anhydrous AlCl3, that is aluminum chloride and HCl gas. The next one is aromatization. Okay, so normal alkanes again having more than 6 carbon atoms. So it should have more than 6 carbon atoms. So aromatization, from the name itself you can say it is going to form aromatic hydrocarbons or aromatic compounds. That means minimum it should have 6 carbon atoms. So 6 or more than 6 carbon atoms it should have. When heated to 600 degrees Celsius at 10 to 20 atm in the presence of oxides of vanadium or chromium or molybdenum supported over alumina give aromatic hydrocarbons. It is also called reforming. Another name is also reforming. So this is called as aromatization. If it is having the alkane, the normal alkane having more than 6 carbon atoms, what happens when it reacts in the presence of oxides of vanadium or chromium or molybdenum supported over alumina? What happens? Yes, you will get an aromatic hydrocarbon. So as you can see here in this case, 1, 2, 3, 4, 5, 6. 6 carbon atom, that is hexane. The normal hexane, when it reacts in presence of these catalysts, you will get the aromatic hydrocarbon, which is benzene in this case. Okay, so this is called as aromatization. Now the next one is reaction with steam. Okay, so methane reacts with steam at 1000 degrees Celsius in the presence of nickel catalyst to give carbon monoxide and hydrogen. It is used in the production of hydrogen gas. So this reaction is also useful in the production of hydrogen gas. So what happens? Yes, methane reacts with steam. Steam is water itself, right? Steam, what happens in the presence of nickel, when it is heated, it forms carbon monoxide and hydrogen gas. So it is this method is also used for the preparation of hydrogen gas. Now the last one is pyrolysis. Pyrolysis or cracking. So what does that mean? The process of decomposition of organic compounds on heating at 500 to 800 Kelvin is called pyrolysis. So what we are going to do here, the higher alkanes, what happens is we are going to break it in presence of very high temperature, or on heating on higher temperatures. What happens? It will decompose into lower compounds. The process of thermal decomposition of alkanes into smaller molecules is called cracking. So if it is done in the presence of high temperature, this is also called as cracking. So pyrolysis means decomposition of alkanes into smaller compounds, and if it is happening in the presence of high temperature, it is called as cracking. So you can see one example here, C6H14, that is hexane. So hexane, if it undergoes pyrolysis at high temperature, so it can form various products. It can form hexene and liberate hydrogen gas. It can form butene and ethane. It can form propene, ethene and methane. Okay, so this is how the pyrolysis will take place. That is, a higher alkane will break down into smaller compounds. Okay, so it can form alkenes and liberate hydrogen gas. It can form further smaller alkenes or smaller alkanes itself. So this is called as pyrolysis. Okay, so I hope the chemical properties are clear for you. So in the next session, we are going to study about the conformations of alkanes. Then we will be moving on to the next one, that is alkenes. So the same procedure we will repeat there as well. That is, first we will study the methods of preparation, nomenclature, then chemical and physical properties. So I hope the topics we have covered in this session is clear for you. So that's all for today. Thank you.